Hi everyone, and welcome back. Today's discussion is going to follow through Chapter 7 of the McMurry Organic Chemistry textbook, available on OpenStax. Chapter 7 is on alkene structure, and this is going to be the beginning of that, where we'll talk about structure and stability, and then we'll get into the rest of it a little bit later. So when we look at alkenes are any compound that contains a C-C double bond. And so shown here are some examples. Simple alkene over here, ethylene. We've got next to that a naturally occurring molecule called alpha-pinene, which is a bicyclic structure, but you can see the alkene functional group right there. And then down below, what we would call a conjugated polyalkene here. So we've got many carbon-carbon double bonds. This is the molecule commonly known as beta-carotene. So where alkenes come from? Well, ultimately, where does anything come from? Nature. We can find lots and lots of alkenes in nature. Two of these examples, of course, come from nature. Pinene is in lots of plants, but including members of the pine family of trees. Beta-carotene is one of the orange pigments that you find in plants. But where most of our alkenes come from in synthetic chemistry is from oil. And so this is a picture of an oil refining plant with these large structures that take crude oil and separate them by a process called ultimately distillation. But what we're doing is we're separating these out, and as a crude measure, we can say separating them by the number of carbons. And so the processes down here are not particularly important to our discussion, but what we can say is that we get some of the very heavy petroleum products. So you'd get coal down here, some heavy oils and things, gas, oil, fuel oil, diesel, kerosene, gasoline, those guys are in here. You may have heard gasoline talked about in terms of octane rating. It's nominally 8 carbons in size. And then we get smaller molecules that come out as gases, literal like gas phase. So things like butane and propane and methane. Well, along the way, we also produce alkenes. And one of the sort of reactions shown in the book is this one, where we're taking hydrocarbons typically in the, so notice N here is up to 6, that's in the middle. So total molecule size, somewhere in the 2 to 8 range. And we can do steam cracking. So high temperature steam will bust up those molecules into all sorts of things, but including ethene and propene and some butene derivatives. So this is an indiscriminate process, very high temperature, no catalysts, no fancy specificity, just high temperature, busting apart hydrocarbons and letting the electrons land where they may. The mechanism here probably involves a radical mechanism like we talked about in an earlier chapter. And so, we could think about here a homolytic cleavage of a carbon-carbon bond at high temperature. Now, we talked before about how that's not particularly stable, and a carbon radical is, amongst the least stable radical we could imagine making. But at these incredibly high temperatures, remember, if we get really high temperature, that can affect our thermodynamics overall here, particularly when we start talking about how temperature affects entropy. So if this happens now, we could imagine losing this other hydrogen over here, producing H2 and reforming a double bond. Forming, I guess I should say, a double bond. So how we use alkenes, all right? So we make them in this indiscriminate high temperature process. We get lots of small molecular weight alkenes like ethene over here. So ethene can be converted to a whole bunch of molecules that have tremendously important industrial value. So if we add water across that double bond, we can produce ethanol, which itself is a valuable material and a precursor for lots of other things. We can put an OH group on both carbons to get ethylene glycol, chlorine in both positions to get ethylene dichloride. If we oxidize this we can go to the aldehyde state or the carboxylic acid or the epoxy state. So we can get these precursors. Acetic acid is one of the largest produced molecules in all of synthetic chemistry. And then there are some other ones here. Polyethylene, we talked before about radical polymerization. If we use ethylene there and we expose it to a radical initiator, we can get polyethylene, which you know probably from different plastics. High density and low density polyethylenes are used commonly in consumer grade plastics. Likewise, we can turn ethylene into vinyl chloride, which when we polymerize that, we get polyvinyl chloride, PVC, which is another plastic that's used in all sorts of things. Vinyl acetate over here, if we were to polymerize that, we get polyvinyl acetate, PVA, another polymer that's used in all sorts of things. If we go up to the 3-carbon alkene, propene, by the same sorts of reactions, can be converted to an alcohol. This is isopropyl alcohol, commonly used in medical clinics as a disinfectant, as well as used in electronics and other things. Again, we can convert it to an epoxy. We can convert it to a plastic, polypropylene polymer. This conversion might not seem so obvious, but it's one that we'll talk about in 238 as well. We can convert it into cumene, which is also one of those natural products found in the cumin seed. So this is one synthetic way to make a natural product, kind of like we talked about at the end of the last chapter. When we start talking about alkenes, one difference, of course, is that we're missing a couple of hydrogens compared to an alkane. And so these molecules are an example of something called an unsaturated hydrocarbon. They have fewer hydrogens than they could have. So fewer hydrogens than the maximum. Calculating degrees of unsaturation is really a useful thing because unsaturations are going to allow us to do some work. Notice that an alkene here has this extra pair of electrons, of course, which we talked about, can be used to go and do some work by reacting with an electrophile. The more degrees of unsaturation we have, potentially the more chemical work we can do. And so degrees of unsaturation, well, in chemistry, we talk about it in those terms, degrees of unsaturation. So we'd say 0 degrees or 1 or 2, or etc. In dietary terms, you've probably heard these words too, particularly when we talk about fats. So saturated fats are those molecules that have a long fatty acid chain like this, and then the acid group at the end, or typically in a biological pH, we'd have the fatty acetate here, the charged version of that fatty acid. Monounsaturated would indicate that we have a double bond in there somewhere, 1 point of unsaturation. And then polyunsaturated would indicate that we have more than one in some positions. And so each of those would have a particular name. If we were to go ahead and add up the pieces of an alkane, right? So we could talk about ethane as an example. We could talk about propane as an example. When you draw those guys out, you'll see that they all have this particular formula whereby we end up with 2 times the number of carbons plus 2 to give us that fully saturated formula. And I like to think about where that formula comes from this way by saying, there's my number of carbons, here's my 2 times. Okay, think about a hydrogen going up and down there, so 2, 4, 6. That takes care of that 2n part of the formula. And then the plus 2, you could think about the hydrogens sort of being on the ends, plus this one and plus that one. Now, of course, if we have a double bond somewhere, we're going to lose 2 hydrogens. And so every 2 missing hydrogens is calculated out as 1 degree of unsaturation. And so if we were to compare, for instance, the formula for ethane to the formula for ethene, we can see we're losing 2 hydrogens. So delta 2 hydrogens, we're missing 2 hydrogens, which means I have 1 degree of unsaturation. Okay. We can calculate that. Here are a whole bunch of varieties here. So Right here at the top is a 6-carbon, fully saturated hydrocarbon, and I've drawn it as the linear hexane. Down below, I have a couple of these that, as we look at the formulas, I go from 14 to 10. So I'm missing 4 hydrogens, which is 2 pairs. So these each have 2 degrees of unsaturation. Okay. And we'll see that we can do that in a number of different ways. We can do it as 2 individual double bonds. Okay, each one of those is a degree of unsaturation. I can do it as a double bond along with a ring, right? Notice if you think about that kind of forming the ring, I'm talking about losing the hydrogen that would have been sticking off here and here as I instead close that ring together, okay? I can think about it as having 2 ring shapes, so that's 2 degrees of unsaturation. Or I can talk about having two pi bonds that are in a triple bond. All right, so when I say a degree of unsaturation, 1 degree of unsaturation is either going to be a pi bond, so part of a double or a triple bond, or it's going to be a ring. Okay, the pi bonds don't have to be between carbons. We could talk about a CO bond as well, but those are your degrees of unsaturation, either a pi bond or a ring. And so if we were to calculate degrees of unsaturation just from a formula, all right, we will need to first think about what would the alkane look like. All right, so we're gonna think about that first using the alkane formula of 2n plus 2 hydrogens for every carbon. Okay, so that is 0 unsaturation, or it's a fully saturated molecule. So we're always going to compare. If it's just a hydrocarbon that we're looking at, that we're evaluating, well, fine, we just look for missing hydrogens. If the molecule we're looking at contains a halogen, we're going to lump those two together when we count up and compare. And this is because halogens bond in the same way as a hydrogen. And so if we count a halogen the same as a hydrogen, the bonding is all going to be the same. The rule for oxygen says that we ignore them. Well, why? Because if we're comparing how a CH would bond normally to how a CH would bond with an oxygen, we can see that same number of hydrogens is there whether the oxygen is present or not. And so we can just ignore the oxygens. And we'll see examples of these in just a second, okay? If we have a nitrogen present in our formula, we have to subtract 1 hydrogen from our count for every nitrogen. And the reason for that is here. Okay, if I have a CH like that compared to a CN, remember nitrogen forms most commonly that kind of a structure. And so by virtue of putting a nitrogen in there, I'm adding 1 more hydrogen than I would have had without the nitrogen. And so we subtract 1 hydrogen for every nitrogen. Essentially, we're eliminating this chunk and getting back down to what it would have looked like without the nitrogen. Let's look at some examples of how to do this in practice. So here are some examples, okay? If I was given this, well, the structure would be easy. I'd say there's 1 degree of unsaturation. It has a double bond. But if I was given the formula C4H8, what I would do here is I would say, okay, let's think about a C4. How many hydrogens would it have if it was saturated? So that's 2n, 2 times 4 is 8, plus 2 is 10. All right, that's where this comes from. This is the fully saturated. And then what I'm going to do is I'm going to say, let's compare these numbers. 8 hydrogens versus 10. I see I have 2 missing hydrogens. And remember, every pair of missing hydrogens equates to 1 degree of unsaturation. Now, just from this formula, C4H8, I don't know if it's this particular alkene here, or if it's an alkene where I had a double bond between carbons 1 and 2, or if it's a ring shape of some kind, right? There's a couple different ways I could do that. Those all have 1 degree of unsaturation. So the formula is not unique, but what it does tell me is that I've narrowed it down to molecules like this instead of molecules that are fully saturated. All right, let's see an oxygen example. Oh no, actually, let's do halogen first. Halogen example. So since halogens bond just like hydrogen, okay, If I was given the formula C4H6Br2, for instance, I would say combine these together and say that's kind of like C4H8. Okay? And again, I would compare that to the fully saturated version. And again, with these numbers in this example, I would say I'm missing 2 hydrogens, which is 1 degree of unsaturation. So the point is, replacing these bromines with hydrogen, or these hydrogens with bromines, makes no difference to the rest of the molecule. So the rule says that I combine all my halogens and hydrogens together and then use that number to compare to my fully saturated. If I have an oxygen, we said before that we're going to ignore them because adding an oxygen doesn't change the number of hydrogens present. And so again, here's the structural formulas to look at. But if I was given a formula like C4H6O, again, that could represent any number of compounds. What I'm going to do is say, I'm going to ignore that oxygen. So I'm going to pretend that it looks like C4H6. I'm going to compare to, the alkane formula. So for a C4 molecule, that would be 10 hydrogens. So in that case, comparing 6 versus 10, I see that I have 4 hydrogens missing. Every pair of hydrogens is a degree of unsaturation, so that's 2 degrees. So again, in this case, the molecule I'm showing you has 2 alkenes in it. So there's 1 degree and the other degree of unsaturation. But I could have had a triple bond somewhere. That would have been both of my degrees of unsaturation right there. I could have had a ring shape of some kind with an alkene. And I guess those are my only 2 possibilities, but there's several isomers of those all that I could draw. And the one that trips people up the most is nitrogen. I have to subtract 1 hydrogen for every nitrogen because every nitrogen ends up bringing with it kind of an extra hydrogen. So see here in the structural formula, if I have an amine like this, and I were to compare that to not having the amine, I can see that I've added in 1 extra hydrogen. And so what I'm going to do here is if I'm given a formula like this, C4H7N, and I'm asked to calculate degrees of unsaturation, what I'm going to do is say, yes, I can take out that nitrogen, but along with it, I have to take out a hydrogen. And so my C4H7N becomes kind of like C4H6. And again, I would compare that to the fully saturated C4 molecule, which would have 10 hydrogens. 10 minus 6 gives me 4 missing hydrogens, or 2 degrees of unsaturation. So along those lines, we can do some practice. Here's degrees of unsaturation, right? So if I was said, how many degrees of unsaturation does this have? I would first remember my rules and say, okay, I'm going to take away that nitrogen and 1 hydrogen. So it's kind of like C6H, not 5, but 4. All right. If this was an alkane, it would be 6. Now it's 2N would be 12, plus 2 is 14, right? I subtract these, 14 minus 4. I get a delta missing 10 hydrogens, which is 5 degrees of unsaturation. Okay, now usually the way I'm going to get 5 degrees of unsaturation, like a whole bunch of unsaturation, that's going to probably clue you that you have an aromatic ring. Because look at this structure right here. That's 1 degree for the ring, plus another 2, 3, 4, altogether 4 degrees of unsaturation for that ring. So that's a really good indicator that maybe that's what I've got going on. Okay. You can do the same sort of thing here, right? So remember the rule for halogens says that I'm going to combine hydrogens and halogens. And so it's kind of like, instead of H9, it's kind of like I'm looking at H12, right? That's 3 plus 9. I'm going to compare that to whatever a saturated 8 carbon would have been. So 2 times 8 is 16, plus another 2 is 18. 12 and 18, the difference is 6. And so That's 3 degrees of unsaturation. Down here, oxygen. Remember, the rule just says ignore it. Ignore the oxygen. And so our formula is sort of like a C7H16, that's 15 plus 1. Compare that to saturated. Now 2 times 7 is 14, plus 2 is 16, and oh, hey, I'm not missing anything. So this is fully saturated, or I could say 0 degrees of unsaturation. And then a simple hydrocarbon down here, I don't have to do anything. I'm just going to compare it to what it should be. 2 times 6 is 12, plus 2 is 14. Now that 14 minus 12 is 2 hydrogens missing, so 1 degree of unsaturation. All right, and again, my text is underneath there, sorry, you can look at the slides. That 1 degree of unsaturation, again, could be a double bond or it could be a ring. And there's several different isomers of each of these. Compared to the fully saturated, again, multiple isomers are possible over there too. All right, so that's degrees of unsaturation. Now that's a really important skill to be able to calculate those because when you do, for instance, molecular analysis later on, one of the first things you'll do is to look at the formula and determine what kinds of molecules you could have, and that helps you narrow down the analysis options that you have to think about. For us right now, we're going to be thinking about it in terms of drawing isomers for a given formula. So if you were, for instance, given this formula number 2 and asked to draw some isomers of it, you would know, okay, 3 degrees of unsaturation, so I've got a ring and 2 double bonds, or a ring and a triple bond, or a triple bond and a double bond, or whatever. There's different options you can get to 3 degrees of unsaturation. So you could draw out molecules that fit that structure. All right, the next thing we want to talk about in this section is to talk about naming. And so that's, let me skip back the text here. Naming and chemical nomenclature is one of the big topics. Obviously, we have to be able to all speak the same language when we're talking about the names of chemicals, so we can ensure that we're all talking about the same things. Alkenes are going to be named just like alkanes were, in that we'll name the parent hydrocarbon. It's going to be the longest chain. We're going to number the carbons so that we get the lowest numbers for our substituents, and we're going to write the name out like we did before with punctuation. However, with alkenes, the longest chain must include the alkene group. Okay, so the alkene gets precedence here. We'll see examples of this in a minute, but you may be able to draw molecules to go in a certain direction that the molecule could be longer if you go in a direction without the alkene. But when there's an alkene present, we're going to take whatever the longest chain is we can get that includes both alkene carbons. And we're going to number the chain in the direction that gives the alkene carbons the lowest numbers first. If there's a tie, where numbering it in 2 different directions gives us the same 2 numbers for our alkene, then we'll go based on the other substituents' numbers. And we're going to include the substituents alphabetically like we always have, but we'll indicate where the alkene is located. And I'll show you what this means. So here's an example. First thing, name the parent hydrocarbon, longest chain including the alkane group. Okay, so if we number in pink, we can see that we get a 5-carbon chain. If we numbered in green, we can see we can actually get a 6-carbon chain, right? 1, 2, 3, 4, 5, 6. However, that doesn't include both carbons of the alkene. So we would not call this a 6-carbon, a hex kind of a molecule. We would call it a pent, a 5-carbon. That's the longest chain we can get going through the alkene carbons, both of them. All right, likewise, numbering the carbons. On the left here, right, we could number from either end, but we want to give priority to our alkene. If I numbered from the left, the numbers I just wrote here, the alkene would be located starting at position 4. If I numbered from the right in the pink, it would be at carbon 2. And so the pink numbers are the way to go here. It gives the alkene the lowest possible number. Likewise over here, we could number from the left or the right, and either way, let me just draw those in, either way our alkene would get number 3, starts on position 3. And since there's a tie in both directions, now we defer to other substituents. There's a methyl group here. And so if we number in pink, that methyl group can get a 2 compared to having to get a 5 in my orange scheme. So the pink numbers would do it again. And then we'll write the name, again, including substituents alphabetically like we've done before, commas between numbers like before, dashes between letters and numbers just like before. However, the ending changes to an ENE to indicate that we have a double bond. Okay, so that's an alkene. So this is a hexene isomer. And the particular one has the alkene starting on carbon 2. So this number always indicates where the alkene functional group starts. So here it's between carbons 2 and 3. We label it as 2-hexene. The other way that you'll see this written is to put the number in the middle of the name. All right. This is actually a more useful way to do it when you get really complex molecules that have multiple functional groups. Is what we're going to see as we see names for alcohols and amines and other stuff, is that you're going to indicate the position of those things as well. And so, so some very complicated looking molecules, you'll have more luck naming it this way, putting the number right in front. So hex-2-ene doesn't roll off the tongue as nicely, but it is equivalent to 2-hexene. Okay. Notice for hexene in particular, we could have had a double bond here instead. So we would have called that 1-hexene, the 2-hexene that we marked here, or we could have had a 3-hexene if we had a double bond there. We can't have a 4-hexene, right? Because if my double bond was here, then I should have numbered from the left, and that's 2-hexene again, right? So because it's a 6-carbon molecule, I can have a 1 or a 2 or a 3 double bond, but I can't have a 4 or 5 or 6. I should have numbered from the other side. Okay. Again, if we have a substituent or multiple substituents, whatever it is, the name is here. 3-hexene would be our parent, and then I have a methyl group at carbon 2. Again, it could have been 2-methyl hex. Now a dash between a letter and a number. Okay, so notice here no space or anything between the L and the H. The letters just flow together. But where I have a letter and a number coming together, that's where I use my dashes. So 2-methyl hex-3-ene would have been an appropriate name for this one as well. All right, here's a couple more examples. Again, we saw this one when we talked about numbering. So even though I could get a 6-carbon chain if I excluded the alkene, my rule says I have to go through the alkene. So 1, 2, 3, 4, 5, I get a pentene. Specifically, it's 1-pentene as my parent chain. And then I have an ethyl group on carbon 2. And again, it could have been 2-ethyl pent dash 1 dash ene. Okay. Just like before, if I have multiple substituents, I would say I have dimethyl or trimethyl, whatever it might be. The same is true if I have multiple alkenes, except that my prefix goes right there. So here, 2-methyl, and it's a 1,3-butadiene. So buta because it's 4 carbons in the parent chain, 1,3 because my alkenes start on positions 1 and position 3, and then 2 double bonds, diene. So you'll see dienes and trienes and tetraenes. So that's just fine. If we wanted to do the other kind of naming that I was talking about, we would put these numbers right there. Buta 1,3-diene. Okay. Okay, and so now we have a couple more examples here. Just following up on that idea, if multiple alkene groups exist, we include that in the name. So again, here's a butadiene with alkenes starting in position 1 and 3. So 1,3-butadiene or buta-1,3-diene if you wanted to use the other format. Here's a cyclopentadiene. So 5-membered ring would make it a cyclopentene if it was just one. Here we have 2 double bonds, so diene is the ending. And again with the numbering, right, we want to number so that the alkenes have the lowest numbers possible, and so we would go that way. Notice that 1 and 2, in a ring like this, 1 and 2 are always going to go through a double bond. So there's no way I would put 1, for instance, here or on either of these carbons. Okay, I could have numbered it across this way or backwards from what I wrote, but it would always be this 1 and 3 relative positioning. And up top here on the right is an example of a triene. So 3 alkene groups positioned at 1 and 3 and 5. All right, and so here's that, sometimes you'll catch us saying the new way of naming it, but it changed in 93, which is not exactly new, but you'll see both of these still very commonly. So the older system would have put the number out front before the numeric, the size of the carbon chain. So 3-heptene here. The newer naming system would say hept and then put the number right before the functional group, so 3-ene. Same thing over here. So 1,4-hexadiene as a parent chain compared to hexa-1,4-diene. Both are acceptable, both are common. When you get to really complicated molecules, the newer system works much better. There are also some common alkenes that have been used for a long time, and they have developed common names. And so this slide is just to make you aware of those. Systematic names are just like you learned for alkanes. So the 2-carbon would be eth, and then now the ene means alkene. So ethene is the systematic common IUPAC name for that. The common name is ethylene, and you'll hear this quite a lot. So that's just a common name. The systematic name is ethene. Same thing here. Prop is our 3-carbon prefix. Ene, that's this molecule on the left, propene. But again, you'll hear it called propylene quite a lot. The 2-methylpropene molecule here, you can see how that functional group would look. So we'd have carbon 1 over here, 2 with the methyl group, and 3. This is an isobutyl arrangement, and it's gotten the common name isobutylene. And then similarly, if we go up to this 5-carbon molecule down here, 2-methyl, so again, carbon 1 right there, 2-methyl, 1,3-butadiene. This is isoprene. So the prenes like this, you might recognize that ending, isoprene and neoprene and chloroprene, different derivatives that have been used in all sorts of things like wetsuits and other stuff. All right. The last little bit that we need to talk about in terms of naming is here in terms of the rigidity of that functional group. Okay, so when we talked about alkanes, we didn't have to talk about conformations, right? We studied conformations, but we said that, butane, for instance, because all the bonds are single bonds, it can rotate freely, and so we don't have to talk about whether it's a staggered or an eclipsed conformation because that's a temporary 3-dimensional arrangement. Alkenes now, we have no free rotation here with a double bond, right? Remember that pi electrons are above and below the plane of the atoms, and so that's limiting our mobility, our rotation around that central bond, around the double bond. And so if we draw it like this versus like this, those are 2 different molecules because of that rigidity. And so we need different names. These are nominally both 2 butenes. We'd have numbering here 1, 2, 3, 4, so double bond at position 2. So they're nominally both 2 butenes. However, we need a prefix to change to indicate which one we're talking about. So cis means on the same side or the same. And so when these substituents are on the same side of the double bond, so if we split the double bond this way, those 2 groups are on the same side, we would say the prefix is cis. Technically, that's written as a lowercase italic, although if you're handwriting it, who can tell? But if you're typing it, that would be a lowercase italic. If they are on opposite sides relative to the plane of or the line of the alkene there, opposite sides would be trans. So cis-2-butene and trans-2-butene. And so some naming examples, right? We want to think about here, what's our longest parent chain? All right, so 2, 3, 4, looks like a 5. And so I'm going to be talking about a pentene. All right, I would number it from the left so that my alkene can get the lowest possible numbers. Remember, alkenes take precedence here, so this is a 2-pentene, right? And then I have methyl groups sticking off of it, so 4, 4, dimethyl 2-pentene. Okay. Likewise, I'll let you number these guys. Remember, when you're talking about a cycloalkene, one of these two carbons will be your carbon 1, and the other one will be carbon 2. So you'd number it 1, 2, 3 going towards chlorine, or 1, 2, 3, 4 going towards methyl. We're going to go this way so that we can get the lowest number for that substituent. Okay, so you can name those out. Oh, and I forgot something. Over here, your stereochemistry, right? I do need to indicate what the stereochemistry is here on this guy. These two groups are going in opposite directions. If I look at the plane of the alkene like that, going down and up here. So I would have prefixed this with trans. Okay, I forgot that. Don't forget that. That's important. All right, the other way around, draw each of the following. Okay, what I think is the easiest way to do this is to think about what's going on and build it up from the parent chain backwards. Okay, so let's look at this third one, 3-hexene, and it's going to be trans. So let's see, I don't know, 1, 2, 3, 4, 5, 6, like that. And then 1, 2, 3, double bond. Well, if I've drawn it like this, I do have a trans orientation. So that's what I wanted, right? And now I've got 2, 2, 5, 5 tetramethyl. So carbon 2, methyl, methyl. Carbon 5, methyl, methyl. And we're done. Now, if I wanted cis, okay, so this is here. If I wanted the cis version of all that stuff up there, I would do the same kind of thing, except this is going to have to point in the same direction as that. Okay, so my double bond is going to look like that. All right, so that's 3, 2, 1, 1, 2, 3, 4, 5, 6. Okay, and then again, methyl, 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 methyl. All right, so this is the cis version over here, trans version over there. Well, what happens if we have more than 2 substituents? Well, I can't use cis and trans anymore. So we have this other system that I think somebody kind of cheekily called EZ. These coming from German words that mean opposite or together. But basically what we're going to do is we're going to split the alkene into its 2 carbons, and we're going to rank the substituents attached to those 2 carbons, just those 2 substituents. We're going to use the same ranking rules that we used for stereochemistry. So ranking by atomic number. And then once we've ranked them, we'll see that each carbon has a lower and a higher ranked. If those 2 higher ranked groups are opposite each other, we're going to put the prefix E. And if those 2 higher ranked groups are on the same side as each other, we're going to use the prefix Z. And a lot of chemists will say it stands for Z same side. However, it probably doesn't. Here are the German words. So the EZ system can always be used. Okay, if we went back here, I could have called this thing on the right, instead of calling it trans, I could have called it E. And instead of calling this one cis, I could have called it Z. And that would have been fine. The EZ system always works. Cis-trans only works if I have 2 only two non-hydrogen substituents. If I've got more than two, I've got to use easy. So here's an example. All right. Now, if I look at this molecule, what's my longest parent chain? 1, 2, 3, 4, 5. It looks like that's about as long as I can get. I would number it from this end so that I can get an alkene starting on 1. All right, so we can do that. So I've got a 1, 3, 1, 3. It's a 5 carbon, 2 double bonds. Okay, 1,3-pentadiene, that takes care of the parent chain part. I've got a methyl group on carbon 3. Okay, so we'll include that guy out front like normal. And then I need to indicate stereochemistry only for the pink one. I don't have to for the black one because this alkene has two hydrogens that are the same. I can't rank these against each other. And so essentially it doesn't matter which way this is connected because it's identical. All right, so I only have to do this when I have more than two different substituents. So the way I'm going to do that here, maybe I can get another color. I'm going to split this down the middle. Okay, I'm going to rank the methyl group versus hydrogen. By atomic number ruling here, carbon would rank first. Okay, so this is my higher substituent on this side compared to the hydrogen. Now when I go over here, now I've got a carbon that I run into in both cases, so we're tied. I need to go out a step further. All right, step further on the bottom, I run into hydrogen. Step further on the top, I run into carbon. So that carbon beats that hydrogen, making the top substituent higher ranking. Since those two high-ranking substituents, the stars I drew, are on opposite sides of the double bond, this is the E isomer. Okay, and so the name would be E 3-methyl 1,3-pentadiene. Notice that the E or Z is going to be in parentheses out front. All right, and so there's my name. Here's another example. All right, so yikes. Well, I need to include my double bonds, right? So it looks like that's going to have to be it right there. That's my parent chain. Again, I'd number from the right. 1, 2, 3, 4. So it's a butadiene now. Right, 4 carbons with 2 double bonds, butadiene. Where are they? Well, located at 1 and 3. It's always the starting position. Now I've got some other stuff attached, which is gross. Okay, so I've got a bromine attached on carbon 1. So that's going to be a 1-bromo. And then this group, give you $1 if you remember what that is, right? That 3 carbons, but attached at the middle carbon is an isopropyl group. And that's attached on carbon 2 of our main chain, right? We're going to alphabetize these guys. The I counts for isopropyl, so B comes first. So see how my spacing is with this weird digital pen. 1-bromo, 2 isopropyl. Oh, not too bad. Okay. 1,3-butadiene, and then out front, I need stereochemistry. Again, I don't have to worry about the 3 alkene here because I have 2 hydrogens. I just have to worry about this one. And so again, we'll go here, we'll split this. By atomic number, bromine way outranks hydrogen. That one was easy. What about over here? Yikes. All right, so if I go out one step, I run into carbon, right? We're tied. The highest thing I can run into now going further out from this carbon, I've got a carbon and another bond to carbon and a hydrogen. Okay, so C, C, H is my kind of ranked list of these 3 things. When I look at this guy, I go out again, C, C, and H. C, C, H. Oh, I'm tied at level 2. Now I go out one further. Okay, and this is where it gets a little tricky. I'm going to say which thing is higher yet, okay? Now, stepping out, I'm going to go to a different color even so we can, there we go. Going out from this carbon, I'd run into 3 hydrogens, right? H, H, H. Going out this way, also 3 hydrogens. So the highest thing I can run into in my next step out, third level now, is a hydrogen. Here, he's got 2 hydrogens, and the third connection is back to that carbon. So as counterintuitive as it seems, there's the rank list. And finally, that carbon beats that hydrogen. So this is my higher ranking group. Since that star is on one side of the alkene and the other star is on the other side of the alkene, this is again an E. Okay. And one more. Again, I know this is maybe belaboring things a little. It's a video after all, you can shut it off if you want to. I need the longest chain I can, including the double bond. All right, so 1, 2, 3, 4. Either way, this is going to be a 2 alkene, right? Whether I number from this side or that side. I would number from the right. 1, 2, 3, 4, so that my little alcohol group down here can get a number 2 priority instead of number 3. Now, we haven't learned how to name carboxylic acids yet, but it turns out that they are even higher ranking group than the alkene. So the name is going to end with the carboxylic acid naming. If this were an alkane down here, no double bond, I'd say buta with an A, noic acid. But you guessed it, with the alkene, I'm going to call it a butenoic acid. That's 4 carbon with an alkene somewhere, carboxylic acid. The alkene is at position 2, okay, right, starting at position 2. And I have this gross substituent attached. Now, there's no easy way to name this thing. So the way it gets named is that it has a hydroxy group attached on what would have been a methyl group. So we call it a hydroxymethyl. Again, don't worry so much about the naming specifics here. This particular one is challenging. The point is looking at the stereochemistry of the alkene. All right, that's why we're doing all this. So again, if we were to rank these, we're going to split the double bond down the middle like that. We're going to rank our hydrogen and our methyl group on the left. Hope it makes sense to you by now that the methyl group outranks hydrogen because carbon's atomic number is higher. Over here, again, first step out, we run into carbon in both cases. However, second step out, I've got 1, 2, 3 bonds to oxygen. This guy's got an oxygen and 2 hydrogens. So its list would look like that, and its list would look like this. And so we're tied so far here, but that oxygen wins. And so we go like that. Our 2 high-ranking groups are on the same side, both on the top, the way it's drawn here. And so that's the same side. Okay, like that. There are some more examples of course, right? Remember, your double bond has to be included in the longest chain. Give it priority. So in this case, carbon 1 would be there. Also, you only need to do the either cis-trans if it's simple, or easy. In any case, you want to do it only if you have 3 or more distinct substituents. So this one, for instance, since these substituents here are both methyl groups, I don't have to give the stereochemistry of this bond. It doesn't matter. I could flip this upside down. It doesn't make any difference. Okay, so I'll let you practice those. And there are the answers, of course. The other way around, right? If we're drawing molecules from their names, Again, start with the back end, right? So start with the parent chain. Maybe we'll do number 2 here. Okay, so if I'm looking at a hexadiene, I would say 1, 2, 3, 4, 5, 6, like that. That's my 6. I've got a hexa now diene at positions 1 and 4. So 1 to 2 is a double bond, and 1, 2, 3, 4 to 5 is a double bond, like that. Now it wanted me to do 4E. This is how we do it if we're trying to be specific about which alkene I'm talking about. Since alkene number 1 here, the way I've drawn it doesn't look like it should need it. I haven't finished this. I guess we'll finish it. 2,4-dimethyl. So 1, 2 methyl, 3, 4 methyl. All right. So now here's our molecule. Notice I don't need to do any stereochemistry for the end because there's 2 hydrogens attached here. So technically this doesn't need a 4. It could just say E because the only one that it applies to is 4. But if I have multiple double bonds that I need to indicate stereochemistry, I would do it out front here, and I would just separate them by commas. So like 2Z, comma 4E maybe, or whatever it might be. But I drew this. Did I draw it right? And that is this actually E around this double bond? Well, you got to make sure, okay? Because I drew it the easy way. I did this sawtooth thing, but as far as ranking goes, again, we'll split the double bond this way. That one ranks higher than the hydrogen that's hiding down here. This long chain is going to rank higher than the methyl group. Those are on opposite sides of this double bond, so that's actually the E. That's what I wanted. Great. If it wasn't what I wanted, then all I would have done is to erase this one right here and draw it down here. Okay, so the point is just draw it some way. Okay, just draw it and then check. And if you're right, that's great. If you're not right, then fix it. Here's some more naming examples, right? So dienes and triene up here. This one's got a ring, so don't forget the cyclo bit. Remember that you always want to number through an alkene on the ring. So 1, 2, 3, 4, 5, 6 would be great going that way. Or you could have started here and gone that way. Either one would have been okay, but you wouldn't start any other place on this ring. Right? So we're going to stop this video here, call that part 1, I guess. So we covered the basics of alkenes, where they come from, what they're for. We talked about degrees of unsaturation, and finally the rules of naming alkenes. We'll pick up in the next video and talk about alkene stability and conformations and stuff, and a little bit about how to explain alkene reactions. So for now, keep up the great work. Email me if you have any questions, and have a great day.